Hello, folks, and welcome to Iron Beetle, a show where we learn how to build a modern distributed database for financial accounting. And actually, no, that is a lie, because the purpose here isn't really to build a modern database for financial accounting, because, to be honest, if you need such a database, you would just use TigerBeetle, of course. Rather, the purpose of what we are doing here every week at 5 p.m. UTC every Thursday for, I think, significantly for, a year and a half already at this point. It's actually different. What we are doing here is we are trying to learn how to build software, because lessons from any specific particular article of software are not that interesting, because the software already is written, it exists, it works, like there is no need to rewrite in a different language or something like that. But the underlying lessons are hugely valuable, and you could apply them to many different situations, many different projects. And today, I think we actually are going to cover a topic which has great applicability. Yeah, let's just do it. Okay, so what are we doing? For the past, many episodes, let me just share my screen so you could see what I'm talking about. Okay, yeah. For the past few episodes, we've been discussing our simulator, like the Whopper, how we could take an entire distributed system and model it faithfully on a single thread on a single laptop. And this gets ridiculously, this gets ridiculous. Last time we actually learned how you could use that same simulator not only to check for correctness of software, but actually to check for performance. We've seen how our rather specific network model allow us to see how the impact of packet loss or different application algorithms results in different time which is required for the cluster to process a set of given transactions. And that's was basically it. So now we know how to simulate software. What we don't know is how you actually run this simulation in practice. And that is somewhat tricky. And this is something what I want to cover today. Okay, and actually, this is also going to be pretty close to my talk on Hybrid Boy 2025. So, okay, this is a simulator. We can run it on a laptop by running a single simple command like, hey, zik build Whopper. It will build the code and then run the simulator once. But obviously, we would want to somehow make sure that this thing is running continuously. So one thing you might want to do here, no, I don't need, where is my browser? I've lost my browser, okay. So one thing you might want to do with the simulator is to integrate it with GitHub Actions. So we have this CI workflow, and you could imagine that somewhere here there is run the simulator step. But there's like two problems here. One is that we generally expect continuous integration to be very fast. Like, you know, our like total run takes 11 minutes, and actually, to my taste, this is pretty slow. I would prefer that to be like, you know, a couple of minutes. But well, it's not too bad. But if you want to run this kind of simulation, of course, you don't want to run it only once. You actually want to run it, I don't know, some significant number of times. And that's just too slow to get on CI. So that's kind of like the first fundamental problem, that we want to run this a lot. We don't really want to settle for running it for 5 minutes or something. The second problem is that thing fundamentally uses random numbers. This thing is fundamentally not trivially reproducible. If you just rerun this command on your computer, you actually would get a different result. If you want to pin result, you need to pass a state explicitly. But well, if you then pass a state explicitly on CI, you always will be running the exact same set of network messages, and you probably wouldn't be exploring the state thoroughly. So what I'm trying to say is that this kind of like workflow, this like continuous integration, GitHub Actions, not rocket science rule, isn't really a good fit for simulation testing. So we need something better. So let's design this thing. So okay, let's start with ourselves. So here we are, happy programmer, and extremely poor illustrator. And we have our laptop. And we kind of like, you know, type on the laptop. We don't want to run our Whopper on this laptop because like laptop is not super fast. Ideally, we want to have a whole bunch of different machines running in the cloud. So that thing should be the cloud. So let's draw it the way clouds are, using like the blue. So okay, this is the cloud. And we want somehow to use our laptop to transfer Whopper to every single one of those like many machines. And that feels like, you know, relatively easy. Like, you know, you could just do something like SCP, which stands for SSH copy, and be done with it. But the thing is, we're probably going to change this Whopper a lot. Like, you know, we start with Whopper 1, and then we realize that, hey, wait a second, we need to add, I don't know, liveness mode here. So then you get like Whopper 2, and it is like, you know, maybe a different color even. And then, like, the next day you realize, wait, actually, I also want to have, I don't know, performance mode. So we have like Whooper 3, and then we need to run this like redeploy procedure many times. So that is already complexity. Okay, what else do we need to solve here? Well, okay, so suppose this Whopper of like whatever version is running, and suddenly it finds a golden seed which fails. So seed equal, I don't know, 92 is kind of like the failure. So we know that this fails. Actually, if it's failed, let's color as red. So okay, like this is, so this machine was running Whopper somewhere in the cloud, and it found a seed. But we need to tell the user that the seed is there. Like we somehow need to transfer this back at the laptop, and we kind of like don't really want to SSH back, because I mean, like my laptop has like all kinds of like things, and okay, so we kind of like we need to build distributed systems here. We need to build like not like the fancy consensus database whatever system, but still we need to build like a boring distributed system which runs computation, which stores data. It's like some kind of like MapReduce cluster thing. And again, the first instinct here for many people would be to reach out for something like Kubernetes or some other kind of like service orchestrator, but not for me, and not for a good reason. Not because like I know Kubernetes very deeply and understand like when it should be used and when it should not be used. It's rather I just don't know this thing. Yeah, for TechCapital we had to invent something simpler. And let me actually show you the result right away. So the result of the system is this DevHub, which shows like which shows the results of various Whopper runs. So for example, this line tells us that there is a pull request number 3008 with this specific commit, and on that specific commit we've run this particular fuzzer. So not the Whopper, we also have like a bunch of like minor fuzzers in addition to Whopper. So we run like some forest. This was the specific command we run on this branch, which you could copy, and it took 41 seconds. And because the color is green, we know that hey, actually this was a successful execution. So this is not a failure. And I'm not sure, I'm not sure if we actually even have some failures here. Oh, okay, yeah. So if we ever get a failure, we'll see something like this. So the same thing, like pull request, commit hash, the fuzzer, and the red coloring of the seed, implying that hey, this particular fuzzer failed. Do we have some other failures except for canary ones? Because okay, not really. Well, that's yeah. This is not a good time to explain this, because we've actually recently fixed all our outstanding Python failures. Our Whopper is completely green, so it is a bit hard to show failures. Anyway, so you kind of get the idea that we kind of like want to have like some sort of a system, and we want to have this kind of GUI on top of this distributed system, and we don't actually want to like make it complex. We want to like do this. Okay, so how are we going to solve it? Well, as usual, as Fred Brooks, I believe, told us that you never should start thinking about software engineering problems in terms of what needs to be done, in terms of actions you need to take, in terms of algorithms. What you should be thinking about is data. What data is input to the system, what data is the output of the system, and what data is stored. So if you look at this UI, you kind of like see that the data here is actually simple. Like the data is basically a set of records, one record for each line of a table, which says like what we've run, how we run it, did it fail, whatever. And you could actually see this data here. So let's see. No, let's take this one. So this seed is 971 whatever. So let's find. So note this is Wilson Forest and branch 3008. So let's find this in the raw data. Okay, yeah. So this is the same data, but as a JSON record. You see that, like, you know, it's like very simple data actually. So our commit hash, our command, our color, green or red, like times to compute the durations, all the stuff. Okay, so where this data is stored? Oh, that's super simple. We store this data in a file called data.json. Not really super imaginative, and that's just a file in the Git repository. So we could actually go and take a bit. Can actually go and clone this repository, although it. Yeah. Okay. So this will take a while because like this repository is actually pretty large. So let's kind of like now that we've seen this thing, figure out what we've done here. So we solved this problem of Wolfram machines communicating the seed to the user. The way we solve this problem is that we have somewhere on GitHub Git repository, which contains this data JSON file. And whenever we find a filling seed, rather than communicating this seed directly to the user's laptop, we go and we git push it to the repository. And so after we pushed it, we get this seed in JSON. Seed into 2 awk false. And awk false is colored red. Okay, so this is actually kind of like, you know, powerful idea. So we need, we have this bunch of machines that are distributed, but they need to, we need to aggregate the data, which is, well, you could say mined on those machines. That means that we need some sort of distributed database. But one very simple distributed database, which you already all know how to use, is just a Git repository. Because Git repository perfectly allows several users to connect to it and distribute better and to push changes. Git repository doesn't really like solve the conflicts for you. So like, you know, if two machines try to edit the same file, they will get a conflict and then we'll need to sort it out, but at least it in general allows you like non-conflicting changes to be merged. So it is aware of multiple users. And that's actually all we need to do here. Like we don't need like fancy CRDTs or whatever, because well, we'll build our super bad CRDT ourselves. Okay, so that is kind of like, you know, now we start seeing parts of the picture of like how we run the Whopper. So we have like this cluster, like which somehow runs some versions of Whopper that is unknown, but then it goes and it puts the results into this Git repository. Then we could have super tiny, let's view page source here. We have super tiny smidgen of JavaScript here, which goes and fetches that data as JSON and then does some like really simple, stupid processing to transform this data into this table. So that's kind of like simple. Well, okay, let me expand on this a little bit. The source code for this JavaScript is right in the main repository in the database. So it is not a separate project. And that's actually quite powerful because that means that if someone on a team doesn't like the way the table is rendered, they can just go and modify code in place as if it was like normal database code, because there is no extra red tape you need to cross. There is no other team, no other repository. It's all directly there. And so just like this JavaScript file, which does all the rendering, which is half 1,000 line of code. And then there is an index, which I believe is, 100 lines. So the 100 lines of JavaScript, 500 lines of, 100 lines of HTML and 500 lines of JavaScript. That's it. So, well, I guess we also have some CSS here, which is, 200 lines of CSS. Why do we need so much CSS here? Well, anyway, I'm not a designer. So anyway, this is powerful because by putting this HTML and JavaScript directly into our main database repository, and well, if someone tells you, no, like TigerBase was written entirely in Zig, you could say, ha 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 ha. They also write some HTML and CSS. Well, anyway, we could deploy this as a simple static GitHub page. So that gives us a very cheap way to build custom UIs for integrating with overall database development process. So for example, you see that besides this table for Fuzzing seeds, on this same web interface, we also have a release manager. So we know that tomorrow, Coolboy22 will be making a release of TigerBeetle. And the next week it will be Chitania. There's also links to, like, pull requests. So instead of doing a stream today, I probably should be reviewing one of those pull requests here. Oh dear, this one is hard. Actually, okay. Do I have new comment from Chaitanya here? Because there was one concern. Okay, yeah, haha. Anyway, so yeah, this is coming back to what I was talking in the beginning, in that we are not really interested in learning about TigerBeetle. We are more interested in learning about building software. This pattern, like this HTML page, is so important. It is so powerful that you should use it for any project which has a team larger than 3 people. Like really, if you are developing some kind of like in-house or open source or proprietary or like whatever project, just build static HTML page with JavaScript for visualizing your internal whatever you need to get visualized. And once you have a page set up, you'll actually realize that, hey, there is a bunch of stuff I want to put there. Okay, so now, how do we actually solve the cloud part here? So we kind of like, so this is, so we know how this thing works. Oh, nice, I can draw this. We know that this is then shown on the nice web page as a beautiful table with beautiful rows, and like some of those rows are red. So this okay, I'm so bad at drawing diagrams, but it is fun. Okay, I'm super bad at drawing, and yeah, so kind of like this is the idea. So it's data JSON. We fetch this into a web page, and the user like looks at this page, and they are like super happy. I don't know how to explain happiness, but this guy over here is like super happy. Okay, so the question is like, how do we manage this? Okay, so here I need a collective noun for whoppers. Okay, so I think the right collective noun for whoppers is swarm. So we need to manage this swarm of whoppers. And as I've alluded to, there are kind of like 2 problems here. One is that just like many physical machines. So we somehow need to repeat this task of spinning up a whopper many times over. So that's kind of like one dimensionality. The second dimension, which is also multiplicative, is that whopper itself changes. We frequently add new logic to it. And that requires us to like change the code which is physically running on the machines, and that is kind of like, you know, also annoying. Like how would you redeploy this thing? And what helps here, like the pattern again, general pattern which you need to be aware is Erlang universal. Yeah, Erlang universal server. This is like one of my favorite blog posts of all time. So this is like super super simple Erlang program, which is an actor which receives a closure through its mailbox, and then it just executes the server. So if we have this server, and then we have this factorial server, what we can do is that we can spawn this universal server and then ask our universal server to become a factorial server. And then it's just another like goes and executes it, and that's it. And this is so powerful. Like this idea that the code can be self-updating, that the only logic that you implement directly is just the upgrade logic, the logic to receive the code and start using this code. And then you kind of like can implement whatever by asking this thing to implement this logic. And again, this is again touching on this idea from the intro that what matters is not a particular software, but the big ideas. Because I mean, Erlang is for like writing telecom switches, which is very different domain from what we are doing. It's like not financial transactions, not accounting at all, not databases. It's like crazily slow, interpreted, untyped, super high level, prolog-inspired programming language. And yet, we are going to take this idea and we are going to use it in Tigerballoon right now. Also, we'll make it so much worse by writing it in POSIX shell rather than in any reasonable language. Okay, so this is the same program we've just seen on late Joe Armstrong's blog, the universal server. So this is how C4 runs, and this is actually what we are running on these machines. So we aren't going to run Whopper here at all. What we are going to run there is a universal server instead, which gives us upgrades. Okay, I'm super bad at. Well, sorry that I waste so much time drawing these things super horribly, but I just love it. I feel like I'm like 5-year-old again. Okay, so universe. That's like big brain idea. We'll be running universal servers on these things. So when we want to upgrade our Whopper, we'll just tell this universal server like, hey, please run this new thing. So this is how this universal server is implemented. This is POSIX shell. And I mean, I wrote significant parts of this code, like the first implementation. This is horrible. Like I hate shell scripts, and it's like it is ridiculous for me to realize that, like, you know, one of my most wildly deployed like real services is written in Bash, but like whatever. So what do we do? We clone the repository, fetch the latest state of the main branch, download Zig, and then run the CFO script, and then loop. Download the repository, update it to the main branch, execute the CFO script, and then loop. Download the repository, switch to the main branch, run the CFO script, and then clone the repository, switch to the main branch, download Zig, run the CFO script, and then loop. So you see, this is every time we loop, we actually get fresh copy of the code, and that way, like, auto upgrade behavior is implemented. So this is powerful. What we do is that we do eventually SSH in SSH into all the services, but we do it only once, which is super important. And we SSH there only to run the script. Then the actual upgrade process, when we change the logic in Whopper, happens automatically as a part of this like clone repository and then loop logic. Do I want to say anything else here? Well, not really. So let's actually look at the actual logic of what we are running. So this is just control. It doesn't specify the actual Fuzzing. The actual Fuzzing is this CFO script. And let's see. Okay, question, like why just call CFO? Why like Chief Financial Officer? Well, because it is continuous Python orchestrator. I wonder, well, let's start with this record. So we have something which is called seed record. And if you remember what we've started with, this seed record is surprisingly reminiscent of the JSON files, JSON records we've seen in this data.json file. And that's because it is. So like you see, okay, now I want this. I still haven't figured, okay, this is embarrassing, but I still haven't figured out how to nicely map macOS Thailand functionality to shortcuts, because I need to the shortcuts to work with like my keyboard, which is this thing, and I need to also make it work with like laptop keyboard with this globe key, and it should work regardless of whether my remapping software Canada runs on a laptop or not. And I'm not smart enough to do this, so that's why I'm kind of like mouse clicking my Thailand, which is super embarrassing. Okay. So you see, commit timestamp, commit hash, fuzzer, okay, count. It's all is really there. Okay, so let's see the logic of this thing. How does it work? And yes, said it is maybe a bit more complicated than it needs to be. But well, we'll manage. So let's start with CLI arguments. First is like budget minutes. Like, how long do we want this script to run? Because like we do want to have auto upgrade functionality. We want to eventually upgrade to newer version, but we also don't want to check for new versions constantly. We do want to like pick a version and let it work for some time, and then after a certain timeout, maybe upgrade. So this budget minutes tells us like how long do we want to run before upgrade, and that is 60. So this thing here is going to run for an hour for shadowing, unless there is a bug in this functionality. And there is a bug in this functionality, but we'll maybe cover this later. So it's going to run for 60 minutes, and then we'll loop. Then we are going to run individual fuzzers. And as usual with, abstract Turing-complete model of computation, there are like 4 outcomes you can observe when you run a certain program, when you run a certain machine. First, it might complete successfully and say, yay, this seed passes. This word belongs to language of the Turing machine. Then it can fail and say, no, this doesn't belong to my language. Then, of course, it can hang. It can take infinite amount of time to do anything. It like enters infinite loop, and I mean that is the thing. The infinite loops in Turing machines might very well be chaotic. So it is not always easy to tell that some code is an infinite loop. It might be like very dynamic. There is not necessarily like a static structure of the infinite loop there. Okay, and finally, like the 4th outcome of a Turing machine, it might end up hidden out of memory. And if it hits out of memory, well, because your machine actually has an infinite amount of memory, that means that Linux kernel's killer is going to kill some other process, some other fuzzer. So that is like what we need to care about. And timeout minutes takes care of that infinite loop case. So if a fuzzer is running longer than 30 minutes, then we assume that this fuzz failure, that this fuzz run is actually a failure. It is a genuine infinite loop. Maybe it's not infinite loop. Maybe like it's just like, our software is super slow. But I mean, if our software is super slow, that's still a bug and we still want to fix it. So that's fine. Finally, there is concurrency. So obviously, every one of servers over here actually has a whole bunch of CPU cores. So if we imagine that this is a CPU, it actually there's like not 2, not 4, not 8 of them. I think not even 16. I think the machines we are running, this all have like 32 CPUs, so it's like a lot of cores. So obviously we do want to take advantage of concurrency here. Okay, then we have a list of our fuzzers. I think this is probably another to do. Minor fuzzers. Okay. Yeah. So we've seen like this Whopper, but there is also, I think, fuzz LSM scan, which is also a Whopper, but which is also a fuzzer, but which targets this particular relatively narrow slice of our database. So particular relatively narrow slice. So this is how we select it. Okay, so let's see. We start our thing. We assume that we are running on a POSIX systems, which I'm not actually sure why we need POSIX here. Maybe it feels like it should actually be running on Redis, but well, doesn't really matter. Do some sanity check for the arguments. Log durations, again, kind of like that's in general, like, another like good general tip. Like whenever you are implementing something, like add internal profiling right from the start. Add ability to software to self-diagnose itself whether it is running slow or fast. Then we print git version because again, if you remember, we are going to ultimately store the outcome of our fuzzing in a Git repository. And we are going to use Git binary to interface with this Git repository. So we do depend on version of Git. And by running this here, we achieve two purposes. First of all, like, directly, we go and print Git version, but actually that's like not really important because honestly, I kind of like don't expect, I've never seen Git breaking backwards compatibility. I've been using Git for more than a decade at this point, and it always was super reliable piece of software. So I don't actually care about Git version. What I do care about though is that I do have a working Git. So the main purpose of this thing is to fail if there is no Git in path. Then we are going to, again, read and write to this repository. So we need some kind of access. And this access is passed as an environment variable. Honestly, I'm kind of like, yeah, not sure why. Well, I think the reason why we are passing this as an environmental variable rather than as a CLI argument is that because the tool we use internally, like Git and GH tool for interfacing with GitHub, also look at the environment. But also, I mean, okay, okay. I feel this is a mistake. We should just use CLI argument here because that would be simple. But anyway, well, we need some access. We take the pattern. Similarly, another feature that is supported by DevHub is that it, like, fuzzes pull requests. And for that, obviously, you need to query GitHub API to figure out what pull requests are available. And we need a separate token there. But again, another important principle, like you should make it easy to run software locally. So if we don't, like Git, we absolutely need, because we use Git to clone the commit we are going to hash, but to fuzz. But for JSON, we actually don't need this. Like, if we don't have it, we could just fuzz the main branch. And that is super important to make this software easy to test locally. So we don't fail here. We just log an error, and that's it. Okay, and similarly, because we depend on this tool, then we print insertion. Okay, then we run our fuzzers, and the only thing we do here is that we specify. I wonder if we should actually do duration here, so you could pass this as budget minutes 60M, just like this budget timeout. Actually sounds reasonable, because, well, you could then do hours perhaps, and then maybe seconds, and maybe nanas, but well, whatever. Okay, run fuzzers. So we have time budget. We need to run fuzzers. And now, okay, so I'm thinking here, because we are, well, okay, let's finish it. It's actually not that much left. So okay, what is what's our overall strategy? So, okay, we have a budget of 60 minutes. We need to run fuzzers. Well, obviously, we want to run the main branch. But on the main branch, we need to run one of our many fuzzers, because if you recall, we have the SAM fuzzer, a tree fuzzer, a Whopper, whatever. And Whopper also actually comes with different configurations. So there is Whopper with main state machine and also Whopper with testing state machine. So there's kind of this thing. Then we want to fuzz pull requests. So there's certain branches which we also want to fuzz. And then somehow we need to store the results in this Git database. And if you think about it, the amount of results is going to be infinite, because like, we run these fuzzers on like many machines, many CPU cores, 24/7. Like if we just record every single seed, that's going to require an enormous amount of data for a really little gain, because we are only interested in failures, and we are not as much interested in successes. Well, I mean, maybe like, we want to count successes. We want to like understand that, hey, actually, like, if we see like 1 million fuzz runs and no failures, it is different information than if we see like 100 million fuzz runs without failures. But main thing is like failures. So how would we do this? And this is, I think, one of the most important realizations I had to make writing this easy. The main idea is that the state of the system is a set of seeds. So if you look here, what is remarkable about this stored data is that it is a flat array. So like, there is no classification, like there's no tree structure here. I don't try to classify seeds by the branch, by the commit hash, by the fuzzer, as you would naturally expect, because, well, there certainly is a sort of like tree structure to the problem, right? There's like branches, and each branch has a bunch of fuzzers, and each fuzzer has like fade-in and pass-in seeds, whatever. And actually, originally I started writing code that way, but then I realized that, hey, this isn't essential, and this actually makes the problem harder. So, and well, apologies for the light theme, but well, today we are going to see a bunch of code in the browser, and in the browser I also use white theme, so that's why editor is also light. Okay, so flat list of seeds. Why flat list of seeds is powerful? Because remember, like, multiple machines produce seeds, and they all want to commit the seeds to the same shared Git repository. And they obviously cannot do this because they will hit conflicts. So like we somehow need to resolve conflicts. And flat list provides a very easy conflict resolution mechanism. Like roughly, what we could do is that you could take the list of seeds and then merge it using merge algorithm. And then, like, obviously we'll get a list twice as long, but then you could actually go and cut half of the list and take only like the first seeds. So this is kind of like the big idea of how you make this, how the data evolves in the system. Like the fundamental construct here is a set of seeds. And a set of seeds has a merge operation, which produces a new set, which is not actually larger than the two sets which were inputs. It is still fixed in size, but which retains only the most important seeds from the original two sets. And this is powerful. That means that because this operation is so weak, because this operation is cumulative and associative and whatever, you actually could very easily do like eventual consistency here. Like you don't care how many machines are running this fuzzer. You don't care, like, maybe like you're running fuzzer on the laptop. It still can produce the seeds. It's like no problem. And you don't care about like, the Git semantics. Like, okay, let's say we like run a fuzzer, we produce some seeds. We want to upload it to Git. We clone the repository, we update the set of files, we upload it, we get merge conflict. Oh, never mind. We just completely kill repository, clone it again, update the seeds again, and upload it. And we repeat it until we succeed, or until we realize that after the merge, we actually removed all our seeds. So there is no need to re-upload stuff. Okay, so let's quickly look at the merge iteration here. Well, merge is maybe less interesting. Like the interesting thing is like org. Like how do we order the seats? So kind of like remember, like we want to keep more important seats. And the first thing we do is that we order by commit timestamp. What is commit timestamp? Well, when you do a git commit, it records a timestamp when this commit was made. And of course, timestamp is not guaranteed to be correct. It's not like Tigerbeetle's cluster time. It can be like very wrong, but in general, it's going to be fine. So you could use timestamps to approximately order commits. And again, because our requirements here are so weak, we don't actually care that the ordering is super precise. Like, okay, let's say that like my time is like 10 minutes later than like Digi's time, and like if we make commits roughly at the same time, and my commit will be newer, although it is older, like no matter, because well, then the next commit is going to be done, and it is going to override this anyway, because like the time always flows forward, and any mistakes will be corrected. Okay, then we order by commit hash, which feels really funny to me because it is just like a tiebreaker. Okay, no, it really doesn't make sense to. Oh, okay, no, it makes sense. So I was going to say it like it doesn't make sense to order by commit hash because, well, I mean, no to commit hashes are the same, so it's just like, you know, everything else doesn't matter. But well, it actually, I mean, you could have several seeds for the same commit, and that is like what you want to group them. So you kind of like you want to keep all the seeds from the same commit together. So okay, then we order by the fuzzer again for the same reason. So kind of like, you know, you see like we do have essentially this hierarchical structure encoded in this linear list of seeds, because we kind of like it is like, you know, it's like incremental number. Like, you know, you first change like the lowest bit, and the next bit, etc., etc. Okay, so then we order by whether the seed is failing or succeeding. And again, like you see, false is less than true. So failing seeds are going to get order before succeeding seeds. Then we order by like basically everything else, and yeah, the actual seed is the tiebreaker. So the seed is guaranteed to be more or less unique. Okay. And then we merge. So merge is kind of like not literally a merge sort, because we have this count field here, which like the semantics is here. So if you have like two successful seeds for the same commit hash, you don't want to just like, you know, take one and drop the other. Like you actually want to know how many successful runs you did. So you take one, drop the other, but then you add counts. So in the merge, we take current seeds, new seeds, concatenate them in a single array, sort them using this comparison function. Okay, so this is. Oh, okay, so. Yeah, okay, so this explains this. So if you look at the dev hub, one of the branches we are always fuzzing is the release branch. And so this is like the release we did last week. So actually, this commit is pretty old. So you see it was made 4 days ago, while main commit was made yesterday. So like normally you would expect recent commit to completely override the release commit, but we kind of like want to actually say, hey, no, if this is like release, then we are going to commit it. So that's why kind of like we rig our comparison function a little bit to keep releases on top. Which makes you realize I haven't explained like one thing here. So we want to keep seeds related to the recent commits. Like, so if there is, like, it doesn't, like, we don't need to know, but like, 2 weeks ago, we had a failure. Like, we don't care. So one would think that it would be enough to only ever collect seeds for the latest commit. Like, when a new commit is made to repository, we start fuzzing that commit and we immediately forget about all the previous seeds. But that is going to be incorrect, because assume that we have a fuzzing failure, which is like really tricky. Like it takes 3 days to hit it. So if you fuzz the same commit for 3 days, you are going to hit this issue. But if you do commits frequently, then once every 3 days, then even if you hit this issue, the moment you get the next commit, you immediately forget about it. So you might not notice the thing. So what you want your fuzz seed visualization to display is to say something like this. Hey, this is the latest commit. And I've been fuzzing this latest commit for 2 hours, and there's nothing there. It is clean. But this is the previous commit. And that commit, I was able to fuzz for 1 day. And I actually found a failing seed there. So either this failure was fixed in the main commit, in the latest commit, or I simply didn't have enough time to find a failure on the latest commit as well. So that is the general idea here. We are going to keep several commits, but not more than 32. So once we go past 32 commits, we will drop the seeds. Okay, so that's basically it. So we kind of like merge this, and then we go through every record, and as soon as we accumulated that many different commits, we stop. We say, okay, so it doesn't matter. We are done. Then we check whether, we are on the same commit and on the same fuzzer. And we count how many seeds we have per fuzzer. And if we have more than 4 seeds for a single fuzzer, we say, okay, no, this is probably okay. We don't care about other seeds. And again, because we sort the seeds such that failures are on top, if there is any failure among the seeds, then it will be in those 4 seeds which are included. But if there is 128 failures, we're still going to keep just 4 of them, because 4 will be enough. And then some logic for merging the counts. And that's honestly kind of like everything that there is to CFO. So there is a bunch of like, like git clone in there, because when you run the puzzle, you want to like run it on specific pull requests. So like you clone the repository, you switch the branch, and then there is like like built-in commands, like whatever. Then there is oh, okay, I'll upload, but well, upload results I will cover somewhat thoroughly, but I want to explain like why we are like skipping like this, like the actual meat, because the actual meat is not that interesting. Like, I mean, you just like spawn a bunch of processes and then you wait them with timeout, and if they fail, you record the failing seeds to these lists of seeds. So that's kind of like super boring. What is interesting is, yeah, periodically you go and you upload the seeds you are accumulated. And the way you do this is that you clone this repository. So this thing. You read the previous seeds, you merge them with the new seeds. This is interesting. So there should be okay. Well, so I was thinking that there should be a loop somewhere which says, hey, if you didn't update the seeds, then don't try to commit anything. But well, I mean, like we don't really need it. So it could be the case that, like, seeds merged is the same that seeds old. But well, if that's true, like, who cares? Like, it's the same. Okay, so we push, and well, we could get a conflict, but then we retry. And the seeds old will be new after a conflict, but seeds new are the same, and seeds merge are different, and that's it. So yeah, that's kind of like it for today. The big idea, like two big ideas. One big idea is that you should have this sort of page for visualizing internal things for your project. And the second big idea is really the universal server pattern, is that if you want to run some kind of infrastructure which needs to be updated, you could wrap it in this sort of script, which like does like git clone, run, loop, git clone, run, loop. And then you'll get out of this for free. And the magic here is that if I want to deploy a new version of the CFO, if I want to deploy a new version of this code which runs Whopper, well, I just push the changes to the repository, and that's it. There's no deploy step. I just commit changes, and then those changes will be automatically redeployed. Okay, folks, I think that's it for today. Let's go to our Iron Beetle to do and mark CFO as done, and see you next week, where we'll pick another item from this list, and I wonder if it would be upgrades. Upgrades are fun. Okay, so next week we are going to pick one item from this list and also explain it. Thanks for watching, and see you in exactly 7 days minus 1 hour. Goodbye.